Okay, now let's get actual thing up and running. As I mentioned earlier, my setup is Windows 11 and WSL running on it. So it will be a bit back and forth between systems and terminals, but I will explain everything as we go. So here you can see the board with a chip connected via USB to my laptop, and it connects in via two ports. This one is connection to the G-Link adapter that will be used to actually program the chip. And this port is port of the chip itself, and this port will be used to talk with host application after device will be programmed. Because device connected to my laptop which runs Linux, let's first check list of the device in Linux, and I'm using a USB IPD program which I mentioned earlier that will allow me to forward USB port from Windows to Linux. And now board is powered off and no device in list. Let's power it on. There is a switch on the board. And now we see that J-Link adapter up and running, and only it, because there is no device from this port, because device is not programmed yet and firmware is not running. But when J-Link port is ready, I can start GDB server, and debugger will use this server to connect to the device and write firmware to the chip. And for the server, I'm using Windows package for G-Link GDB server. And here is the port that this server will open for the debugger itself. Let's run it. We see here that device connected, device properly recognized, but no debugger connected yet. So now when it's ready, we can switch to Linux and actually compile and write firmware to the device. But first let me show you the main demo script that will run host application. So main parts here are mnemonics, and this mnemonics will be used to initialize device and then to derive keys and address. Password I just left blank, and this is derivation path for keys and addresses. And for this path I already prepared a so-called wallet or just address which has some IDO on it, so we can build balance and submit transactions using this address. And this is address of the script that will be sort of on-chain store for device sensor readings that will be sent through UTXO to the script address. And the rest part is configuration, the network. We're gonna use path to node socket, device port. This device port will appear in the system after we program and start device and mode of operation, which is submission or verification, and we start with submission first, so later we can verify data from the chain. We can check address to make sure there is no UTXOs on it and we're running everything from scratch. I'm using Cardano CLI here, and there is no UTXO at address now. And I can actually verify the same with Cardano scan, for example. So there is nothing on it. Let's proceed to actually flashing the device. You see another terminal open here. This terminal will be used to program the device. And let's quickly check this directory. The important part here is this config.toml file. It has configuration for cargo run command, and what will happen after I execute cargo run, it will run GDB multi-arch debugger that will connect to GDB server, and it will use this script to actually load compiled firmware on the device. And script is here in the device directory. So let's check it out. Here we can see command to connect to GDB server, and because GDB server in my case running on Windows and the rest stuff running on Linux, I'm using the IP of my Windows machine, but if you run everything on the same system, you can just put port here. Next, 3 commands: enable logging, and you can search for semi-hosting to get more details. But in short, there is a special commands like print statements that I put in firmware, and we will be able to see these print statements in the terminal as host application makes request to the device. Then this command will load firmware to the device, and here it will start execution of the firmware. So let's actually run everything. Here from Embedano device directory, I execute cargo run, which will run our runner with debugger. And you see that firmware is sent to device now. And if we switch to GDB server again, we see that debugger is now connected. I didn't hear USB connection sound, and it sometimes happens when I first flash a firmware after device was completely wiped out. And just to make sure, yeah, there is nothing new here. Let's try one more time. It usually works. Yeah, now I hear USB connection sound, and if we go to device list, we can see that new device appeared. It's serial port COM6, and now I will forward this port to WSL instance using this ID here. Let's check. We see that device is marked as attached now, and we can verify it in Linux. And this is the device port. So this is device that runs on this USB port that connected to the chip. And as the last preparation, I need to give reading and writing rights. This will be the port in the system, so I will give it read-write rights. And check. Everything looks fine, and now host application should be able to use this serial port to communicate with the device. So now let's finally run everything. This is a demo script that will launch host application, and here I'm passing this serial port, and here is submit mode, so it will build and submit transaction. We see things start to talk to each other. First, host application initializes the device and request sensor readings from it. And here we can see logs from the firmware on the device side that device was successfully initialized. The temperature is 25 Celsius. This is the timestamp that host application sent to the device, and now device signing data and sending everything back. And it takes some time on my system, I suspect because of this USB forwarding from Windows to Linux. And if this is a single system, it usually takes just a couple seconds. Now, after host application received sensor data, it started to build transaction, and for that it requested public key from device, and we can see logs from the device side that it sends a public key to the host application. And again, it takes some time on my setup. Now, when public key was received, host application built and balanced transaction, calculated transaction ID, and now it asked device to sign actually this transaction ID, and we can see corresponding logs on the device side. So after transaction ID was signed, host application finished building signed transaction and submitted this transaction to the chain. And this is ID that we can check. But meanwhile, let's submit one more transaction just to have like couple UTXOs to verify later. And here you see again, host application requests temperature data. There is new temperature the same, but timestamp is new. So signature will be also new. And let's see if previous transaction was submitted or propagated already. It's not yet. Let's just wait a bit. Here is process still going. Now we proceed to building transaction. Let's check previous transaction again. Okay, it was submitted to chain, and we can examine it. Let's check UTXOs, and if we go to the UTXO and inspect datum, we will see the data in datum, which is temperature reading, timestamp, and signature produced from the temperature and timestamp, and this should be the same data that we got from the device and host application. And here second transaction is almost done, so let's just wait a bit and then verify that script address has both UTXOs before we proceed to verification part. I will grab this ID to check it when everything will be done. Okay, second transaction also submitted. Let's wait a bit while it propagates on chain. Meanwhile, we can, for example, check script address through Cardano CLI. Let me check if this is correct address. Okay, from Cardano CLI, we see that both transactions actually landed. This is the first one. with two ADA just to add some minimum ID required and inline datum, and this is second transaction. We can print it a bit. And we can see same readings that we saw on Cardano scan, the temperature readings, timestamp, and the signature. And probably this transaction should be available at Cardano scan already. Yeah, this is it. So both transactions were signed by the device and submitted to chain by host application, and that's it for submission. And next we go to verification part. For the verification part, let's change setup a bit. Firmware is already loaded on the device, so we can see how device works alone without any debugger. There is switch on this development board that will power off everything but the chip and some buttons. So let's toggle it. We see now there is no light anymore on J-Link adapter, but to be extra sure, we can just unplug cable here, and we can even unplug this cable to simulate sort of new connection. Let's check device list, and I'm sorry, last time I said that this is Linux terminal. This is actually Windows terminal, and it shows devices connected to the Windows on my laptop because this is the first system that device get connected to. So let's check device list. There is no J-Link adapter or device with COM port 6 that was available before. So let's connect the board. We see now COM port 6 is available again, and this is the cable that connected directly to the chip that runs firmware. And now I will forward it again to my Linux system. Here in Linux system, I will check that device is available. And it is here. And again, I will check that port is available for read write, and it's not. Let me fix that. Now everything looks okay, and I will start submission demo script, again providing the path to the port, and now command is verify. So what happens now is host application start to talk to the device. It initialize device and request public key from the device for derivation path and password that was specified before. And there is no debugger output this time on the left side because nothing connected but USB device itself. And after host application will receive public key from device, it will query script address, take two UTXOs that there at the moment, so it's done now. Let's see it step by step. Here host application received public key from the device. Then here it queried two UTXOs and parsed the inline datums, extracting temperature, timestamp, and signature from them. Then host application combined temperature and timestamp exactly the same way as device does it before signing to get array of bytes. And then using public key it received from the device, it checks that this combined data is actually a response to this signature, and this will like prove that this data was submitted with the device initialized with same mnemonic and password. And to show it briefly, this is the host part where it parses inline datum. Here it combines timestamp and temperature, and then here public key verifies data and signature obtained from inline datum also. And we can sort of unplug the device and make sure nothing works now. So that's actually it for verification and for the demo. All links I mentioned there will be added to milestone 3 example application document here, together with links to Cardano scan for transactions and script address, and everything is located in Embedano repository. That's it. Thank you for watching.